Hi, this is Ms. Varka, and I'm going to run through your Chapter 4 practice problems. You'll need a couple of things for this work today. One is you'll need your Plainsman periodic table, which you got this week in class. And you'll also need to print out the Chapter 4 practice problems or recreate this grid and each of the problems below on a piece of paper. So I might pause the video and get those things and come back in just a second. All right, welcome back. Let's look at the Chapter 4 practice problems. We're going to start by writing shorthand notation for each of the elements that I have listed in the grid here, and then determine the correct number of protons, electrons, and neutrons found in the most common isotope. So I'm going to start with iron, and to give you a better sense of what I'm going to put right into here, I'm going to write it on a whiteboard. So for iron, I need to find iron on the periodic table, and it's right here. It is a chemical symbol Fe, and so I am going to write Fe, which is the chemical symbol for iron. Uppercase F, lowercase e. And then when we write shorthand notation, the requirements are very specific. What we want to do is to write the mass of iron as, instead of a decimal, we want to write it as a mass number. So in order to do that, we're going to take a look at iron on the periodic table. We'll find the mass number here, which is 55.8. I'm sure it's focusing in. It's on yours. You should be able to see that. And I'm going to round 55.8 to the nearest whole number, which is 56. And it goes in the upper left. So that is a superscript to the left of the chemical symbol for iron, Fe. Then I'm going to find the atomic number, which is a whole number on our periodic table. It's in green and it's in the upper left of the box that has the information about the element. And that atomic number goes in the lower left. So it's going to go here. Now the atomic number is very specific to each different element, and it tells us the number of protons that we have for that particular element. So this would be the shorthand notation for iron. So I'm going to transfer that to my worksheet here. And it's going to look like this. Iron in its chemical symbol, which is uppercase F, lowercase e, 56 in the upper left and 26 in the lower left. Now, there's no line between those. It's not a fraction or anything like that, and those should always be whole numbers. Now, if we look at that, then to determine the number of protons, we know that the atomic number is the number of protons. So we write 26. And just in case you are ever not sure, the atomic number key on our periodic table, you can see in the key in the bottom, it tells us our atomic number in the boxes on our periodic table are in green in the upper left, and they will always be a whole number. Okay, so that's looking at the periodic table. Then if I look at my shorthand notation, the atomic number will be shown to the lower left in shorthand notation. Now, number of electrons for iron. We know that that is going to be the same as the number of protons if we have a neutral atom. So we're going to show that as 26. Okay, same number of electrons as protons. That's why an atom is neutral. Protons are positive, electrons are negative. We have the same number of protons as electrons. We have a neutral atom. The next part is the number of neutrons. So for this one, I want you to always write down your calculation. We're going to round the atomic mass to the nearest whole number, which we've already done here in our shorthand notation. So I'm going to write down number 56 and then subtract from that the number of protons, which is 26. So my number of neutrons equals 56 minus 26, which is 30. You're always welcome to use your calculator to double check that. And I'm going to add in the symbol for each of these. So 26 protons, I show protons as P plus. 26 electrons, electrons are E minus. So the lowercase letter that starts the subatomic particle, and then the charge. And then for neutrons, there are 30 neutrons, that's lowercase n with a 0 to indicate no charge, neutral subatomic particle. Okay. I'm going to give you some time now to do the same process for yttrium. And sometimes the hardest thing with yttrium is finding it on the periodic table. So I'll give you a hint. It's over here in this area. So you're going to do this same process. I would like you to pause the video and we will then start up again after you have completed the shorthand notation, number of protons, number of electrons, and number of neutrons. Okay, so you should have completed for yttrium. You saw that yttrium has an atomic number of 39. We put that in the lower left for our shorthand notation. And then when we see its mass number as 88.9, we round that to the nearest whole number, and that will give us a mass number for the most common isotope. So that's a process you're going to need to be familiar with. So this would be the shorthand notation for yttrium. And so you should have that in your worksheet or on the work that you're doing for submitting here. Now for protons, we know that the atomic number is the number of protons, so that's 39. For electrons, same as the number of protons when we have a neutral atom, so also 39. And then to get the number of neutrons, we take the mass number and subtract this number for it. So there's kind of a nice trick that you should know. If you have these set up correctly in shorthand notation, then if you subtract the lower number from the upper number, then this should give you the number of neutrons. So that's also another way to realize just exactly, number of neutrons. That should give you the idea that you are setting this up correctly. Okay, so that gives us 50 neutrons for yttrium. Okay, so you should check and correct. And now let's go on to zinc. So zinc is our next element. For zinc, we're going to find it on the periodic table. It is right here. So pause the video and complete this activity for zinc. Okay, for zinc, you should have found that zinc with atomic number 30, that goes here, and 65.4 rounds to the nearest whole number of 65. So this is your correct shorthand notation. That tells us, of course, that zinc has 30 protons and 30 electrons, since protons and electrons are going to be the same number in a neutral atom. And when we take 65 minus 30, we get 35 neutrons. Okay, so the mass number is actually the number of protons plus the number of neutrons. So double check that and make sure that you get to the mass number of the most common isotope. The next element that we're going to look at is californium, and it's here at the bottom. It's atomic number 98, so way toward the bottom of your periodic table. Go ahead and pause and complete this exercise for californium. Okay, so for californium, which we can see here as atomic number 98, that means that our shorthand notation, which is composed of the chemical symbol of the particular element with the atomic number of protons in the lower left, and then we round our atomic mass, in this case is 251.1, we round that to the nearest whole number. Remember, 251, the mass number is the number of protons plus the number of neutrons. So in order to find your number of neutrons, we take 251 on our calculator and subtract 98. and that gives us 153 for our value for the number of neutrons. So in our worksheet here, we would say protons, again, 98, the same as the number, atomic number. That's what it tells us, the number of protons. That means that there would be 98 electrons when we have a neutral atom. And when we subtract 98 from 251, we get 153 neutrons. So an overview here is that when we are writing the shorthand notation, it consists of our chemical symbol for a particular element with the atomic number, the number of protons in the lower left, and the mass number, which is going to be a whole number. So we take for the most common isotope, we round to the nearest whole number from the mass value that's given on the periodic table. Now we're going to look at your next part, which is determining the average weighted atomic mass for an element. So look at the next part of your video worksheet, of your worksheet, where it tells us that we're going to determine the average mass for an element. All right, part 2 of our video is we're going to be determining the weighted average mass of these mystery elements. We have 2 elements, element A and then element B is on the next page. Now this is looking a little bit blurry, but you can see this on the worksheet or you can print this out. So what we have is an element that has 3 isotopes, and the mass of those 3 different isotopes are given. So that means we have an element that has, of course, the same number of protons. That is what makes these isotopes the same element, but they have different number of neutrons, which changes the mass. The abundance of the different neutrons is shown here. So we can see that this isotope that has a mass of 31.972 is actually the majority. So we would expect when we come up with our value for this to be very, very close to 32. So that's just kind of setting us up to make sure that we're working with this correctly. So the first step in this process is to get the values of mass times abundance for each of these different isotopes. So I'm going to come up with a calculator value that I'll write in here, and then I will be adjusting for sig figs to put into the second value. So in your calculator, you would plug in 31.972 and multiply that mass times the abundance. So the abundance is 94.93. And we get a value with the calculator that is this. Okay, so I'm going to write that out, 3035.10196. Now we can see that that's a lot of significant figures. So we want to determine where our significant figures are for this value. So if we look back at our values that we're multiplying, we can see that this value has 5 sig figs and this value has 4 sig figs. So we want to round this to 4 sig figs, which is going to be to this value. So we'll get a value of 3,035. We'll do the same for the next 3 values. So I want you to do that and adjust for sig figs. If you're working with pencil, then you'll be able to change if required as you're doing this adjustment. Okay, so I've gone ahead and done the calculations for isotopes B and C, and I want to talk through this with you as we look at the calculator values and the significant figures. So for this isotope A, we said we needed 4 sig figs, so we rounded that to, or we looked to the digit after the 5, it doesn't round the 5 up, so we end up with 3,035. For the next one, here's our calculator answer, 25.05796. And let's see about significant figures. Now here we have 5 significant figures, and here we have 2 significant figures. Remember, lefty zeros are not significant. That means that our solution needs to be rounded to 2 significant figures. So we look to the place after the 5. These will be our 2 significant figures. And we see that the 0 does not round the 5 up, so we get 25. Now for this next one, here's our calculator value. We have 5 sig figs here times 3 sig figs here. So our answer needs to have 3 sig figs. So those will be in these 3 places. We look to the place to the right of the 5, and the 7 indeed rounds that up. So we have 146. Okay, so those are our values of, if we had a sample of 100, this would be the mass of these 94.93. This would be the mass contributed by 0.76 of this mass value. And this would be the mass contributed by 4.29 of this mass value. So in order to get the total mass for these 100 atoms, potentially, we need to add those together. So that's what this sum part is, the sum. We're going to add together 30.35 plus 25 plus 146 to get the mass of those 100 atoms. So you go ahead and do that and come up with. Okay, so for that value, when I add those together, I get 3,206 AMUs. That's the mass of 100 atoms. Since we're trying to find the weighted average mass for one atom of this element, we're going to divide this by 100. So 3,206 divided by 100. That will give us a mass value of 32.06 AMU for this particular element, which we said earlier it should be pretty close to 32 AMUs. So that is the case. Now we want to determine the identity of the element and get to that and show this value again. Okay. So in order to find the identity of the element, we want to search through the masses of all the elements on the periodic table until we get to the value that is very close to this. Okay. So here we're at phosphorus with 31.0, and here's sulfur with 32.1. The 32.1 that is sulfur on this table is the closest value to this. So I would say that this is sulfur as the element, and that our calculated atomic mass, average weighted atomic mass with the data that we have, is 32.06 AMUs. And that's because we had data that was very specific and had masses that had been measured to many places past the decimal in terms of AMU. Please do not change your value here to the value that's on the periodic table. The Plainsman periodic table, all of these values are worked with data that rounds to the 10th of an AMU, whereas we calculated this with the data that was given to the 100th of an AMU. Now, using that same method that we just did for element A, we're going to work with element B. So I'm going to talk you through it a little bit and then give you some time to work on it. First of all, element B, we can see has 5 different isotopes, and the isotopes range in mass from 57.935 up to 63.928. We can see that the most abundant of the isotopes that we have is has 68.08%, and that is the 57.9. So we would expect this to be fairly close to 58 AMU, although we can see that we have quite a few that are above that, so it's definitely going to be higher. Remember that your steps include multiplying the mass value here times the abundance and getting a calculator value. Then adjusting that for correct significant figures. Do that for each of these isotopes. Then you're going to add together these values and come up with a sum that is the mass of 100 atoms if we were to have an element that had isotopes in this ratio. Then we're going to divide that by 100 to find the mass of just one atom, okay? Remembering that the units are AMU. And then lastly, go to the periodic table to identify the element and write the average weighted atomic mass that you calculated. I'm going to pause the video and you can go ahead and do that work. Okay, so you should have this work done. And I'm going to talk through the rest of this. So taking this mass value times the abundance, we get this value in the calculator. If we look at our original values, we need to take 5 sig figs times 4 sig figs, meaning that our solution needs to have 4 sig figs. So that's going to be 3,944. Same thing here with B, mass times the abundance, and that's 5 sig figs times 4 sig figs. So this value will be rounded to 1,571. For the next one, we can see that when we take this value times this value, our solution is going to need to be shown with 3 sig figs. So we are going to look at our value here. Let me double check this number. 60.931 times 1.14. And we get 69.46134, which rounds then for 3 sig figs. This value rounds the 4 up to a 5, so 69.5. Then we get our value here that we need to round to 3 sig figs. So the 7 rounds the 4 up, 225. And then I purposely left this last one blank because when we multiply these two, we get this value, and we need to round that to 2 sig figs. So we're going to look to the value that's to the right of the place that we're going to have the second sig fig. So we have this and this. We're going to look to the 4, and the 4 does not round the 9 up. So we don't go the 5 rounds the 4 and then the 4 rounds the 9. The 4 is less than 5, so it does now not round the 9 up. So that means that we have these values that we're going to add together. Now, hopefully when you added these together, you went ahead and did so, and then realized that your calculator answer is going to include a 0.5, and yet the 0 places past the decimal are going to be what determines the significant figures here. So we can see here that our value of 5,868.5 needs to be round to 0 places past the decimal. So the 5 will round this up, and we'll have a value of 5,869 AMUs for these 100 atoms. So that's the total AMUs for those atoms. Now we are going to divide that by 100. So we'll take our 5,869 divided by 100 equals 58.69 AMUs for one atom. Okay. So now to identify the element, of course, we look at our periodic table, and we're looking for a value that is in the 58.69 range. So here I'm coming across 50.9, 52.0, 54.9, 55.8, 58.9, 58.7. So if you were comparing cobalt and nickel here, nickel with 58.7 is much closer to the value that we had than cobalt 58.9. So that means that this element is nickel, and that the average weighted atomic mass that we've solved for is 58.69 AMU, which matches very closely with the average weighted atomic mass that we have on our Plainsman periodic table. Go ahead and complete these worksheets and submit them.